a question that has haunted humanity since we first looked up at the night sky. Is space infinite? Does it stretch on forever in every direction, without limit, without boundary, without end? For centuries, this seemed like the only reasonable answer. After all, what could possibly exist beyond space? How could nothingness have an edge? The very idea felt absurd, almost childish. But recent discoveries have shaken that certainty to its core. Scientists now have compelling evidence that space is not infinite, that the universe has a shape, a structure, and yes, potentially an edge. Not the kind of edge you can stand at and look over, but something far stranger and more profound. If this sounds impossible, if it challenges everything you thought you knew about reality, then you're starting to grasp just how revolutionary this idea truly is. If you want to explore this mind-bending concept with me, hit that subscribe button, and let's dive into one of the most profound questions science has ever confronted. To understand why the idea of a finite universe is so shocking, we need to first appreciate just how deeply infinity has been woven into our thinking about space. The concept feels almost self-evident. You imagine yourself floating in the void, looking in any direction. What stops you from going further? What wall could possibly exist? And if there were a wall, what would be on the other side of it? These questions seem to demand infinity as the only logical answer. For most of human history, this intuition went largely unchallenged. Ancient philosophers debated the nature of space, but the idea that it might simply end somewhere felt nonsensical. Even as astronomy advanced and we began mapping the cosmos with increasing precision, infinity remained the default assumption. Galaxies stretched outward in every direction we looked. The more powerful our telescopes became, the more galaxies we found. Each new discovery seemed to confirm that space was limitless, that no matter how far we traveled, there would always be more to explore. This assumption became so ingrained that it stopped being a question and started being a foundation. Cosmologists built their models on it. Physicists wrote their equations assuming infinite space. The mathematics worked beautifully, the observations fit. There seemed to be no reason to doubt it. But science has a way of revealing that our most obvious assumptions are often the most dangerously wrong. The first crack in this certainty came not from observation, but from theory. In the early 20th century, Einstein's general relativity revealed something extraordinary about space itself. It was not a fixed stage on which events unfolded. It was not an empty container waiting to be filled. Space was dynamic, flexible, capable of bending and stretching and evolving. More importantly, the equations of general relativity allowed for solutions where space was finite, yet had no boundary. This sounded like a contradiction. How could something be limited but have no edge? The answer lay in geometry itself. Imagine an ant walking on the surface of a sphere. The ant can walk in any direction, as far as it wants, and it will never encounter a wall or an edge. Yet the surface is clearly finite. There is only so much sphere to explore. This is because the surface curves back on itself. The ant is confined to a two-dimensional surface embedded in three-dimensional space. Now, extend that idea. What if our three-dimensional space curves in a higher dimension we cannot perceive? What if the universe wraps around itself in a way that makes it both finite and boundless? This was not idle speculation. Einstein's equations explicitly permitted such geometries. In fact, they suggested that the shape of space depends on its energy content. If the universe contains enough matter and energy, it could curve back on itself, forming what mathematicians call a closed geometry. Think of it like the surface of a sphere, but extended into 3 dimensions. A spaceship could travel in what seems like a straight line, and eventually return to its starting point without ever encountering an edge. This idea was mathematically elegant, but for decades it remained purely theoretical. There was no way to test it. The universe was so vast that even if space curved, the curvature might be too subtle to detect. We would be like ants on an enormous sphere, unable to perceive the curve because we can only see a tiny patch of the surface. But then something changed. We developed tools capable of measuring the large-scale structure of the universe itself. The breakthrough came from studying the oldest light in existence. Shortly after the Big Bang, the universe was filled with extremely hot, dense plasma. As it expanded and cooled, that plasma eventually became transparent, releasing light that has been traveling through space ever since. Today, we detect that light as the cosmic microwave background radiation, a faint glow coming from every direction in the sky. It is the afterglow of the universe's birth, and it carries information about the fundamental structure of space. When scientists first measured this background radiation in detail, they noticed something remarkable. The light showed tiny fluctuations, small variations in temperature across different regions of the sky. These fluctuations were not random. They had a pattern, a structure that encoded information about the geometry of space itself. By analyzing these patterns, cosmologists could determine whether the universe was flat, open, or closed. The measurements were extraordinarily difficult. The fluctuations were incredibly small, less than 1 part in 100,000. Separating the signal from noise required years of painstaking work and instruments of almost unimaginable sensitivity. But eventually, the data began to tell a story. The patterns in the cosmic microwave background suggested something unexpected. Space appeared to be flat, or at least very close to flat on the scales we could measure. At first, this seemed to support the idea of an infinite universe. Flat space extends forever, with no curvature to bring it back on itself. But there was a problem. The measurements were not perfect. They had uncertainties, margins of error, and those uncertainties left room for a small but significant amount of curvature. More importantly, even if space is flat on the largest scales we can observe, that does not necessarily mean it is flat everywhere. It could be that the universe is so large that its curvature is too gentle to detect, even with our best instruments. This is where things get truly fascinating. Some cosmologists began exploring a radical possibility. What if the universe is finite but so large that its curvature is nearly imperceptible? What if we live in a cosmos that wraps around itself, but on a scale so vast that we cannot yet see the evidence directly? This idea is not just speculation. It is grounded in serious mathematical modeling and supported by subtle hints in the data. One of the most intriguing pieces of evidence comes from what scientists call topological features. Topology is the study of shapes and how they connect, independent of size or exact geometry. A finite universe with a specific topology would produce distinctive patterns in the cosmic microwave background, patterns that arise from the way light wraps around space. If the universe is smaller than the observable universe, light from distant objects could have traveled around space multiple times, creating duplicate images or correlated patterns in different parts of the sky. Researchers have searched for these patterns, The results are tantalizing but not yet conclusive. Some studies have found hints of correlations that are difficult to explain if space is truly infinite. Others have found no such evidence. The debate continues, but the mere fact that we can search for these features represents a profound shift in how we think about the universe. Infinity is no longer the default. It is a hypothesis to be tested. Another line of evidence comes from the large-scale structure of the universe itself. Galaxies are not distributed randomly. They form intricate patterns, vast filaments and voids that stretch across hundreds of millions of light years. These structures form through gravitational collapse over billions of years, and their distribution depends on the initial conditions of the universe and the geometry of space. By mapping these structures in exquisite detail, cosmologists can infer properties of space that are otherwise invisible. Some models suggest that if space has a finite volume, the distribution of galaxies would show subtle statistical anomalies, deviations from what we would expect in an infinite universe. Again, the evidence is not definitive. The universe is complex and many factors influence galaxy formation. But the possibility remains. Each new survey, each more detailed map brings us closer to answering the question. What makes this search so difficult is that we are fundamentally limited by the observable universe. Because light travels at a finite speed and the universe has a finite age, there is a boundary to what we can see. Beyond a certain distance, light has not had time to reach us. This creates a horizon, a limit to observation that has nothing to do with the actual size of the universe. We cannot look beyond this horizon, no matter how powerful our telescopes become. This means that even if the universe is finite, it might be larger than the observable universe. We could be living in a cosmos with an edge that lies forever beyond our reach, or the edge could be closer than we think, just waiting to be discovered in the patterns of the cosmic microwave background or the distribution of galaxies. The uncertainty is maddening, but it is also what makes the question so compelling. The implications of a finite universe are staggering. It would mean that space itself has a finite volume, a specific amount of room for stars, galaxies, and everything else to exist. It would mean that if you traveled far enough in one direction, you might eventually return to your starting point, having circumnavigated the entire cosmos. It would mean that the universe is not an infinite expanse, but a closed system, a finite arena in which all of cosmic history unfolds. But what would this edge actually be? This is where intuition fails us completely. We cannot think of it as a wall or a boundary in the traditional sense. There is no surface marking the end of space, no barrier preventing you from going further. Instead, the edge is a feature of geometry itself. It is the point where space curves back on itself, where traveling forward becomes traveling backward, where the concept of direction loses its usual meaning. To grasp this, we need to abandon our everyday experience of space. We live in a world where edges are real, where boundaries are physical. A room has walls, a continent has shores, even the earth has a surface. But the universe is not contained by anything external. It is all there is. If it is finite, the finitude arises from its own internal structure, not from being bounded by something outside. This is why the question of whether space is infinite or finite is so profound. It is not just about measuring distances or counting galaxies. It is about understanding the fundamental nature of reality itself. And the answer, whatever it turns out to be, will reshape how we see ourselves and our place in the cosmos. For now, the evidence remains inconclusive. Some measurements suggest flatness extending to infinity. Others hint at subtle curvature that could close space into a finite whole. The debate continues, driven by ever more precise observations and ever more sophisticated models. But one thing is certain. The question is no longer purely philosophical. It is scientific, testable, and possibly within reach of being answered. And that changes everything. If the universe is finite, if space truly has a boundary of some kind, then we are forced to confront a reality that defies our deepest intuitions. The cosmos is not an endless void, but a finite structure with specific properties and limits. What happens when we push against those limits? What lies at the edge, if there is one? And what does it mean for us, for our future, for the ultimate fate of everything that exists? These are the questions that drive the search forward, and the answers, when they come, will be among the most important discoveries humanity has ever made. Understanding whether the universe is finite or infinite requires grappling with geometry in ways that stretch the mind. Most of us grow up with an intuitive sense of space as flat and extending forever. We imagine a vast emptiness that goes on without end, like an infinite sheet of paper stretching in every direction. This picture feels natural because it matches our everyday experience. Walk in any direction on Earth, and absent obstacles, you can keep going. Look up at the night sky, and there is no hint of an edge, no suggestion that space might curve back on itself. But geometry, the mathematical study of shape and space, reveals that this intuition is limited. There are other possibilities equally valid that produce very different universes. To explore these, scientists rely on concepts that were developed over centuries by mathematicians trying to understand the properties of different types of space. The key insight is that space can have different geometries depending on its curvature. In a flat geometry, the rules we learn in school apply perfectly. Parallel lines never meet. The angles of a triangle add up to exactly 180 degrees. Distances follow the Pythagorean theorem. This is Euclidean geometry, named after the ancient Greek mathematician Euclid, who codified these rules more than 2,000 years ago. For centuries, it was assumed that this geometry described physical space. But Einstein's general relativity revealed that space can curve, and when it does, Euclidean rules break down. There are three basic types of curvature that space can have: positive curvature, negative curvature, and zero curvature, which corresponds to flatness. Each one produces a different kind of universe with different properties. Understanding these differences is essential to grasping what it would mean for space to be finite. Start with positive curvature. This is the geometry of a sphere's surface, extended into 3 dimensions. In this geometry, parallel lines eventually converge. The angles of a triangle add up to more than 180 degrees. Most importantly, space has a finite volume. A universe with positive curvature is closed. If you travel far enough in any direction, you eventually return to where you started. Just like walking around the Earth brings you back to your starting point. This type of space is finite, but has no edge. There is no boundary, no place where space ends. It simply wraps around on itself. Now, consider negative curvature. This is the geometry of a saddle or a hyperbolic surface. In negatively curved space, parallel lines diverge. The angles of a triangle add up to less than 180 degrees. Unlike a sphere, negatively curved space extends infinitely. It has infinite volume and no boundary. This geometry produces an open universe that goes on forever, but with a very different structure than flat space. Finally, there is flat space, the geometry we are most familiar with. Flat space also extends infinitely in all directions. It has zero curvature, meaning that Euclidean rules apply everywhere. Like negatively curved space, a flat universe has infinite volume and no edge. For decades, determining which of these geometries describes our universe was one of the central goals of cosmology. The answer depends on the density of matter and energy in the universe. General relativity tells us that matter and energy curve space-time. If there is enough stuff in the universe, its gravity will curve space into a closed, positively curved geometry. If there is too little, space will have negative curvature and remain open. And if the density is exactly right, space will be flat. This critical density is incredibly small, only a few atoms per cubic meter on average, but it is the difference between an infinite universe and a finite one. Measuring the geometry of space is extraordinarily difficult. We cannot step outside the universe and look at its shape from the outside. We can only make measurements from within, using light and matter as our probes. The cosmic microwave background provides one of the best ways to do this. The patterns of temperature fluctuations in this ancient light are sensitive to the curvature of space. By analyzing these patterns in exquisite detail, scientists can determine whether space is flat, open, or closed. The results from missions like WMAP and Planck have been stunning. They show that the universe is remarkably flat, with curvature consistent with zero within the measurement uncertainties. This suggests that if space is curved, the curvature is so slight that it is nearly impossible to detect, but nearly flat is not the same as perfectly flat. The uncertainties in the measurements leave room for a small amount of positive curvature, enough to make the universe finite. This is where the concept of topology becomes crucial. Topology is the study of shapes and how they are connected, independent of their exact geometry. Two shapes are topologically equivalent if you can deform one into the other without tearing or gluing. A coffee cup and a donut are topologically the same because both have one hole. A sphere and a cube are topologically equivalent because neither has holes. Topology focuses on global properties rather than local details. Applied to the universe, topology asks a different question than geometry. Geometry tells us about curvature, about how space bends locally. Topology tells us about the overall structure, about how space is connected on the largest scales. A flat universe can have different topologies. It could be infinite, extending forever in all directions. Or it could be finite, wrapping around on itself in specific ways. These are called flat tori, and they are perfectly consistent with zero curvature. Imagine a two-dimensional example. A flat piece of paper extends infinitely. But if you take a rectangular piece of paper and glue opposite edges together, you create a torus, a donut shape. The surface of this torus is still flat locally. If you were an ant living on it, you could not detect any curvature by measuring triangles or angles. But the space is finite. Walk far enough in one direction and you return to your starting point. This is a flat, finite space with a non-trivial topology. The same idea applies in 3 dimensions. Space could be flat yet finite, wrapping around in ways we cannot directly perceive. Different topologies predict different patterns in the cosmic microwave background and the distribution of galaxies. If the universe is smaller than the observable universe, we might see repeated patterns or correlated structures in different parts of the sky. Researchers have searched for these signatures, and while some studies have found tantalizing hints, the evidence remains inconclusive. The challenge is that the universe might be so large that even if it is finite, the size exceeds the observable universe. Light has only had about 13.8 billion years to travel since the Big Bang, and during that time the universe has been expanding. This creates a horizon beyond which we cannot see. If the universe's true size is larger than this horizon, we cannot directly observe its finite nature. We would be like inhabitants of a giant sphere, so large that the surface appears flat no matter how far we look. This brings us to a profound realization. The question of whether space is infinite might be fundamentally unanswerable from our position in the cosmos. We might be forever limited by the observable universe, unable to probe beyond the horizon. The true size and shape of space could lie forever beyond our reach, leaving us to infer its properties from subtle clues and indirect evidence. Yet this does not mean the question is unscientific or unimportant. Even if we cannot observe the entire universe, we can constrain its properties. We can measure curvature with increasing precision. We can search for topological signatures. We can test different models and see which ones best fit the data. Each advance narrows the possibilities and brings us closer to understanding the fundamental structure of reality. Moreover, the question has profound implications beyond cosmology. If space is finite, it changes how we think about existence itself. A finite universe has a specific volume, a definite amount of space for matter and energy to occupy. It suggests that the cosmos is a closed system, bounded not by walls but by its own geometry. Everything that exists, everything that has ever happened or ever will happen, unfolds within this finite arena. On the other hand, if space is truly infinite, the implications are equally staggering. An infinite universe contains infinite possibilities. Every possible arrangement of matter, every conceivable history occurs somewhere. You exist not once, but infinitely many times, in infinitely many variations. The concept is dizzying and challenges our notions of uniqueness and identity. The geometry of space also affects the ultimate fate of the universe. In a closed universe with positive curvature, expansion might eventually slow, stop, and reverse, leading to a big crunch where everything collapses back into a singularity. In a flat or open universe, expansion continues forever, and the cosmos grows increasingly cold and empty as stars burn out and galaxies drift apart. The shape of space is intimately connected to its destiny. All of this depends on precise measurements of curvature and careful searches for topological features. The tools to make these measurements are improving rapidly. Next-generation telescopes and satellite missions will map the cosmic microwave background and the distribution of galaxies with unprecedented detail. These observations will either confirm that space is flat to within even tighter limits, or reveal subtle curvature that points to a finite universe. For now, the question remains open. Space might extend infinitely in all directions, or it might curve back on itself, forming a finite whole. The answer is written in the structure of the cosmos, encoded in the light from the early universe and the arrangement of galaxies across billions of light years. We are tantalizingly close to reading that message, to understanding one of the deepest truths about the reality we inhabit. And when we finally do, it will represent one of the greatest intellectual achievements in human history. While geometry and topology provide the mathematical framework for understanding whether space is finite, the real evidence comes from observations. Scientists must look at the universe itself and search for clues that reveal its true nature. This is where the cosmic microwave background becomes indispensable. It is the oldest light we can observe, a snapshot of the universe when it was only 380,000 years old. At that time, the cosmos was a hot, dense soup of particles and radiation. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms. This process, called recombination, made the universe transparent for the first time. Photons that had been constantly scattering off charged particles were suddenly free to travel through space. Those photons have been journeying across the universe ever since, and today we detect them as a faint microwave glow coming from every direction. The cosmic microwave background is remarkably uniform. Its temperature is the same to within 1 part in 100,000 no matter where you look, but there are tiny fluctuations, slight variations in temperature from one region of the sky to another. These fluctuations are not random. They represent density variations in the early universe, regions that were slightly denser or less dense than average. Over time, gravity amplified these variations, turning them into the galaxies, clusters, and cosmic structures we see today. The pattern of these fluctuations contains a wealth of information. By measuring them precisely, cosmologists can infer the composition, age, and geometry of the universe. Missions like COBE, WMAP, and Planck have mapped the cosmic microwave background with extraordinary precision, revealing details that were unimaginable just a few decades ago. These maps show a universe that is flat to within a fraction of a percent. The data fits beautifully with models assuming zero curvature. But small uncertainties remain, and those uncertainties are critical. Within the margin of error, the universe could have a slight positive curvature, enough to make it finite. Detecting such curvature requires incredibly precise measurements. The Planck satellite, launched by the European Space Agency, provided the most detailed map of the cosmic microwave background to date. Its measurements constrained the curvature parameter to an extraordinary degree. But even Planck could not rule out a small amount of positive curvature definitively. Beyond curvature, cosmologists search for topological signatures. If the universe is finite with a non-trivial topology, it could produce distinctive features in the cosmic microwave background. One possibility is called the circles in the sky signature. If the universe is smaller than the observable universe, light from the Big Bang could have traveled around space and reached us from multiple directions. This would create matching circular patterns in the temperature fluctuations, circles that appear in different parts of the sky, but are actually images of the same region viewed from different angles. Researchers have searched for these circles and found intriguing but inconclusive results. Some studies reported potential matches, but further analysis suggested they could be statistical flukes or artifacts of how the data was processed. The search continues using ever more sophisticated algorithms and larger data sets. Each new analysis refines our understanding and either strengthens or weakens the case for a finite universe. Another approach involves studying the large-scale structure of the universe. Galaxies are not distributed uniformly. They form a cosmic web, with vast filaments of matter separated by enormous voids. This structure formed over billions of years through gravitational collapse, and its statistical properties depend on the initial conditions set by the Big Bang and the geometry of space. By mapping the positions of millions of galaxies, astronomers can measure correlations and clustering on different scales. If the universe is finite, these correlations might show anomalies. For example, if space wraps around on itself, the distribution of galaxies could exhibit periodic patterns or unexpected symmetries. Detecting such features requires analyzing enormous data sets and accounting for numerous complicating factors like galaxy evolution, observational biases, and cosmic variance. Surveys like the Sloan Digital Sky Survey and upcoming missions like Euclid and the Vera Rubin Observatory are providing the data needed for these analyses. One particularly intriguing line of evidence comes from studies of the cosmic microwave background's large-scale patterns. Some researchers have noted that the fluctuations on the largest scales, corresponding to regions of the sky separated by more than 60 degrees, appear weaker than expected. This is called the low quadrupole anomaly. If confirmed as a real feature rather than a statistical fluke, it could suggest that the universe is finite and not much larger than the observable universe. In such a scenario, the largest fluctuations would be suppressed because there simply is not enough space for them to develop fully. Similarly, other studies have examined the alignment of certain features in the cosmic microwave background. Some patterns seem to align with each other in ways that are statistically unlikely if the universe is infinite and isotropic, meaning the same in all directions. These alignments could be coincidences, or they could hint at a preferred direction or axis in the universe, possibly related to its finite size or topology. The challenge with all these observations is separating signal from noise. The universe is complex, and many factors can produce patterns that mimic the signatures of a finite space. Cosmic variance, the fact that we have only one universe to observe, makes it difficult to determine whether an unusual feature is meaningful or just a random fluctuation. Statistical rigor is essential, but so is caution. Extraordinary claims require extraordinary evidence, and the question of whether space is finite certainly qualifies as extraordinary. Recent advances in computational cosmology have helped. Scientists can now run detailed simulations of universe formation under different assumptions about geometry and topology. By comparing these simulations to real observations, they can test which models best fit the data. These simulations reveal that subtle differences in curvature or topology leave distinct fingerprints in the cosmic structure. The challenge is achieving sufficient precision in both simulations and observations to detect these fingerprints reliably. One fascinating possibility involves gravitational waves. These ripples in space-time, first detected in 2015, provide a new way to probe the universe's structure. Gravitational waves from the early universe, if detected, could carry information about the geometry of space. Missions like LISA, a planned space-based gravitational wave observatory, might be able to detect these primordial signals. The patterns they produce could reveal whether space is flat, curved, or has a non-trivial topology. Another promising avenue involves neutrinos. These elusive particles interact weakly with matter and can travel vast distances unimpeded. By studying the distribution of neutrinos across the universe, scientists hope to gain insights into cosmic structure formation and the large-scale properties of space. Neutrino detectors are becoming more sensitive, and future observations could provide complementary evidence about the universe's geometry. Despite all these efforts, the question remains tantalizingly unresolved. The current data slightly favors a flat, infinite universe, but the uncertainties leave room for alternatives. A small positive curvature cannot be ruled out. Non-trivial topologies remain possible. The universe might be finite, with a size just beyond our current ability to measure. Or it might be infinite, extending forever in all directions. Both possibilities are consistent with what we observe. This uncertainty is not a failure of science. It reflects the profound difficulty of the question and the limitations of observing from within the very system we are trying to understand. We cannot step outside the universe and examine its shape from an external vantage point. We are confined to our cosmic horizon, limited by the finite speed of light and the finite age of the universe. Everything we learn must be inferred from signals that reach us across billions of light years. Yet, progress continues. Each new observation refines our understanding. Each improvement in technology brings us closer to answering the question. The cosmic microwave background is being mapped with ever greater precision. Galaxy surveys are covering larger volumes of space. Gravitational wave detectors are opening new windows on the cosmos. Computational models are becoming more sophisticated. All of this work is converging on a single goal: determining whether space is infinite or has an edge, whether the universe is truly boundless or finite. The answer, when it comes, will transform our understanding of reality. If space is finite, it means the cosmos has a specific structure, a definite size, and a particular topology. It means there is a limit to how much universe there is, even if that limit is unimaginably vast. And it raises new questions. What determines the size? Why does space have the topology it does? Is there something beyond the edge, or does the concept of beyond lose meaning when space curves back on itself? If space is infinite, the implications are equally profound. An infinite universe contains infinite possibilities and challenges our notions of uniqueness and meaning. It suggests that the cosmos has no center, no special place, and no overall shape in the conventional sense. It forces us to grapple with the idea that everything that can happen does happen somewhere in the vastness of infinite space. For now, we live in the uncertainty, in the space between knowing and not knowing. But that space is narrowing. The tools are in hand. The observations are being made. The analysis is ongoing. And one day, perhaps soon, we will finally know whether the universe we inhabit is finite or infinite. That knowledge will be among the most important humanity has ever gained. It will tell us not just about space, but about existence itself. The question of whether space is finite is not just a matter of geometry and measurement. It has profound philosophical implications that touch on the nature of reality, existence, and our place in the cosmos. If the universe is finite, it means there is a specific, limited amount of space. Everything that exists, everything that has ever happened, and everything that ever will happen is contained within this bounded arena. The cosmos is not an endless expanse, but a closed system with definite properties. This idea challenges our intuitions in fundamental ways. We are accustomed to thinking of space as something that simply is, a passive backdrop against which events unfold. The notion that space itself might have a boundary, even if that boundary is expressed through geometry rather than a physical wall, forces us to reconsider what we mean by existence. If there is a finite amount of space, then there is a finite amount of room for matter, energy, and structure. The universe is not just large. It is specifically sized, with limits that, in principle, could be measured and understood. One of the deepest implications involves the concept of infinity itself. Infinity is a mathematical abstraction, a useful tool for describing processes that continue without end. But does physical infinity actually exist in nature? A finite universe suggests that it does not, at least not in the spatial sense. Space, the most fundamental aspect of physical reality, would be limited. This does not mean infinity disappears from physics. Time might still be infinite. Mathematical infinities remain essential for calculations. But the physical arena in which everything happens would be bounded. This has implications for questions about uniqueness and repetition. In an infinite universe, probability takes on strange properties. If space extends forever and matter is distributed even somewhat uniformly, then every possible arrangement of particles occurs not just once, but infinitely many times. There are infinitely many regions identical to our solar system, infinitely many Earths, infinitely many versions of you. The idea is both fascinating and deeply unsettling. It suggests that nothing is truly unique, that every moment and every choice is repeated endlessly across the infinite expanse. A finite universe avoids this conclusion. If space has a limited volume, then the number of possible configurations, while astronomically large, is not infinite. There is only one of you, or at most a small number scattered across the cosmos. Uniqueness is restored. Your existence becomes more than just one instance in an infinite series. It is a singular event, unrepeated and irreplaceable. For some, this is comforting. It suggests that life and consciousness have a special status, that they are not diluted by infinite repetition. But finitude raises its own questions. If space is limited, what determines the size? Why is the universe as large as it is and not smaller or larger? These questions do not have obvious answers. In cosmology, the size and structure of the universe are thought to emerge from the conditions of the Big Bang and the subsequent expansion. But why those particular conditions? Physicists speak of initial conditions and fundamental constants, but the ultimate origin of these properties remains mysterious. Some theorists have proposed that our universe might be part of a larger multiverse, a vast ensemble of universes with different properties. In this view, the size and geometry of our particular universe would be somewhat arbitrary, just one possibility among many. The multiverse concept is controversial and difficult to test, but it provides a framework for thinking about why our universe has the specific features it does. If there are many universes, each with different sizes and geometries, then our finite universe might be just one among countless others. Another philosophical implication involves the ultimate fate of the cosmos. If the universe is finite and closed with positive curvature, its long-term evolution might differ dramatically from that of an infinite, open universe. A closed universe could eventually stop expanding and begin contracting, leading to a big crunch where all matter and energy collapse back into a singularity. This would be a reversal of the Big Bang, a cosmic cycle that ends where it began. In such a scenario, time itself might be finite, bounded on both ends. In contrast, a flat or open infinite universe expands forever, Stars burn out, galaxies drift apart, and the cosmos becomes increasingly cold, dark, and empty. This is sometimes called the heat death of the universe, a state of maximum entropy where no further useful work can be done. In this scenario, time extends infinitely into the future, but the universe becomes ever more desolate. Which fate awaits depends on the geometry and energy content of space, questions still being actively researched. The finiteness of space also affects how we think about exploration and the future of humanity. In an infinite universe, there are always new frontiers, new regions to explore, new possibilities to discover. No matter how far we travel, there is always more. A finite universe, by contrast, is ultimately exhaustible. There is a limited amount of space to explore, a finite number of stars and galaxies. In principle, if civilization endured long enough, it could map the entire cosmos, reaching every corner and understanding every structure. This does not mean exploration would become trivial. A finite universe could still be unimaginably vast, far larger than anything we could explore in any practical sense. But the principle is different. The cosmos would be a bounded domain, a finite puzzle with edges and limits. This changes the nature of cosmic ambition. Instead of endless expansion into infinity, the goal might become complete understanding of a finite whole. There is also a psychological dimension. Humans have long been drawn to the infinite, the boundless, the eternal. Infinity represents freedom from constraint, a sense that possibilities are limitless. A finite universe imposes limits, even if those limits are so distant as to be nearly irrelevant to everyday life. For some, this might feel claustrophobic, a kind of cosmic confinement. For others, it might be reassuring, a suggestion that the universe is comprehensible, that it has a definite structure we can hope to understand fully. The question also intersects with existential and theological considerations. Many religious and philosophical traditions have grappled with concepts of infinity and eternity. The idea of a finite universe fits more naturally with certain cosmologies, while an infinite universe aligns with others. Science does not settle these deeper questions, but it informs them by revealing the physical structure within which all human thought and experience occur. Perhaps most profoundly, the question of whether space is finite or infinite reflects back on the nature of scientific inquiry itself. Science seeks to understand the universe through observation, experiment, and reason. But we are finite beings with finite tools and finite lifetimes, trying to comprehend a cosmos that might be infinite. Even if we cannot observe every part of the universe, even if some aspects remain forever beyond our reach, we can still ask meaningful questions and draw valid conclusions from the evidence we have. The search for the edge, or the confirmation of infinity, is driven by a deep human need to understand our place in the grand scheme of things. Are we inhabitants of a finite cosmos, bounded but vast? Or do we live in an infinite expanse that extends forever in all directions? The answer will not change our daily lives in obvious ways, but it will profoundly shape how we see ourselves and the universe we inhabit. This is why the question matters, why scientists devote careers to mapping the cosmic microwave background and measuring the curvature of space. It is not just about numbers and equations. It is about understanding the nature of reality at the most fundamental level. And as we stand on the threshold of potentially answering this ancient question, we confront both the power and the limits of human knowledge. The universe may or may not reveal all its secrets to us, but the act of searching, of pushing the boundaries of understanding, is itself profoundly meaningful. Looking forward, the quest to determine whether space is finite or infinite is entering a new phase. Advances in technology and observational techniques are providing scientists with unprecedented tools to probe the structure of the universe. The next generation of telescopes, or satellites and detectors, promises to deliver data with a precision that would have seemed impossible just a few decades ago. This progress brings us closer to answering one of the oldest and most fundamental questions humanity has ever asked. One of the most anticipated developments is the James Webb Space Telescope and its successors. These instruments can observe the universe at wavelengths and sensitivities that reveal details invisible to earlier generations of telescopes. By studying distant galaxies, the large-scale structure of the cosmos, and the properties of light from the early universe, these observatories will provide new constraints on the geometry and topology of space. Every observation adds another piece to the puzzle. Ground-based observatories are also advancing rapidly. Projects like the Vera Rubin Observatory will conduct massive sky surveys, mapping billions of galaxies and tracking changes in the cosmic web over time. These surveys will allow scientists to measure the distribution of matter with unprecedented accuracy, revealing subtle patterns that could indicate whether space is curved or has a non-trivial topology. The sheer volume of data will require sophisticated machine learning algorithms and computational techniques to analyze fully. In addition to electromagnetic observations, gravitational wave astronomy is opening entirely new windows on the cosmos. The detection of gravitational waves from merging black holes and neutron stars has already revolutionized astrophysics. Future detectors, both on the ground and in space, will be sensitive to a broader range of frequencies. These instruments might detect gravitational waves from the early universe, carrying information about the conditions moments after the Big Bang. Such signals could provide direct evidence about the curvature and expansion history of space. Neutrino astronomy represents another frontier. Neutrinos are ghostly particles that interact so weakly with matter that they can travel across the universe almost unimpeded. Large detectors, often located deep underground or under ice to shield them from cosmic rays, are capturing neutrinos from distant astrophysical sources. As these experiments grow in scale and sensitivity, they could provide complementary data about cosmic structure and the properties of space. All of these observational advances are supported by theoretical progress. Cosmologists are developing more sophisticated models of the universe, incorporating insights from quantum mechanics, particle physics, and general relativity. These models make specific predictions about what we should observe if space is finite or infinite, flat or curved. By comparing model predictions to actual data, scientists can test different scenarios and narrow the range of possibilities. Computational simulations play a crucial role in this process. Modern supercomputers can simulate the evolution of the universe from the Big Bang to the present, tracking the formation of galaxies, the growth of cosmic structures, and the behavior of dark matter and dark energy. By running thousands of simulations with different assumptions about geometry and topology, researchers can identify the signatures that distinguish one type of universe from another. These simulations are becoming so detailed that they can reproduce the observed universe with remarkable fidelity. One area of active research involves refining measurements of the Hubble constant, the rate at which the universe is expanding. Different methods of measuring this constant have yielded slightly different results, a tension that has puzzled cosmologists. Resolving this tension might require revising our understanding of the universe's composition or evolution, and it could have implications for the question of whether space is finite. If the discrepancy points to new physics, it might also point to subtle curvature or topological features. Dark energy, the mysterious force driving the accelerated expansion of the universe, is another key piece of the puzzle. Understanding dark energy's properties and how it affects the geometry of space is essential for determining whether the universe will expand forever or eventually collapse. Missions dedicated to studying dark energy, such as the Euclid satellite and the Nancy Grace Roman Space Telescope, will measure the expansion history with unprecedented precision. There is also the possibility of surprises. Science often advances through unexpected discoveries, observations that do not fit existing models and force researchers to rethink their assumptions. A clear detection of topological signatures in the cosmic microwave background, for example, would be a game changer. It would confirm that space is finite and has a specific structure, opening up entirely new avenues of research. Even negative results, increasingly precise measurements that rule out certain types of curvature or topology, are valuable. They narrow the space of possibilities and guide future investigations. Beyond the technical aspects, the quest to understand space's finitude is reshaping how scientists think about cosmology itself. It encourages interdisciplinary collaboration, bringing together experts in general relativity, quantum field theory, observational astronomy, data science, and more. It also fosters international cooperation, as major projects require resources and expertise from institutions around the world. The question is too big for any one nation or group to answer alone. Public interest in these questions is also growing. Cosmology has always fascinated people, but recent discoveries and media coverage have brought it to a broader audience. Documentaries, popular science books, and online content are helping non-specialists appreciate the profound nature of these inquiries. This cultural engagement is important because it sustains support for the basic research needed to answer such deep questions. Education and outreach are essential components of this effort. Training the next generation of scientists ensures that the quest continues. Universities and research institutions are developing new courses and programs focused on cosmology, data analysis, and computational methods. Young researchers bring fresh perspectives and innovative approaches, often seeing connections that more established scientists might miss. As we look to the future, it is worth reflecting on how far we have come. A century ago, the idea that we could measure the curvature of space or map the entire observable universe would have seemed like fantasy. Today, it is routine science. The tools we have developed, both conceptual and technological, are extraordinary. They allow us to peer back in time to the earliest moments of the universe, to measure distances across billions of light years, and to test fundamental theories with exquisite precision. Yet, for all this progress, the ultimate question remains unanswered. Is space infinite or finite? Does the universe have an edge? And if so, what does that edge mean? These questions drive us forward, compelling scientists to push the boundaries of knowledge ever further. The answers, when they come, will be among the most significant discoveries in human history. They will tell us not just about the structure of space, but about the nature of existence itself. In the meantime, we live in a time of extraordinary exploration. The universe is revealing its secrets, piece by piece. Each observation, each measurement, each theoretical insight brings us closer to understanding the cosmos in its entirety. The journey is long and the challenges are immense, but the destination is worth every effort. To know whether space is infinite or finite is to know one of the deepest truths about the reality we inhabit. And that knowledge, once gained, will forever change how we see ourselves and our place in the universe. The possibility that space might have an edge, or that it might be finite but without a boundary, forces us to confront the limits of language and intuition. Our everyday experience provides no guide for thinking about such concepts. We live in a world where everything has clear boundaries. A room has walls. A planet has a surface. Even the Earth, though round and lacking an edge in the usual sense, is clearly finite. But the universe is not contained by anything. It is all there is. If it is finite, that finitude must arise from its own internal structure. This is where geometry becomes not just a tool, but a way of seeing. The curvature of space determines its global properties in ways that defy simple visualization. We cannot draw a picture of curved three-dimensional space because we are embedded within it. We cannot step outside to look at its shape. All we can do is make measurements from within and infer the structure from those measurements. It is like being a character in a book, trying to deduce the shape of the page from the words printed on it. Yet, this limitation does not render the question unanswerable. Mathematics provides a language for describing things we cannot visualize. Equations can capture the properties of curved space, predict observable consequences, and guide us towards understanding. This is one of the great triumphs of modern science, the ability to reason about phenomena that lie beyond direct experience. Consider the analogy of a sphere again. An ant walking on the surface of a sphere experiences a two-dimensional world. The ant cannot perceive the third dimension into which the sphere curves. Yet, by making careful measurements, the ant could deduce that its world is finite. If the ant walked far enough in one direction, it would return to its starting point. If the ant measured the circumference of circles and the areas they enclose, it would find that these measurements deviate from the flat geometry it might intuitively expect. The ant could infer the curvature of its world without ever seeing the sphere from outside. We are in a similar position. Our three-dimensional space might curve in a higher dimension we cannot perceive, but we can make measurements within our three-dimensional space that reveal this curvature. The cosmic microwave background, the distribution of galaxies, gravitational waves, all of these provide data that encode information about the global structure of space. By analyzing this data with the tools of geometry and statistics, we can infer whether space is flat, curved, finite, or infinite. This process is not easy. The measurements are difficult, the data is noisy, and the models are complex. But it is possible. And that is what makes the question so compelling. We are not asking about something forever beyond our reach. We are asking about something we can, in principle, discover through observation and reason. This quest is not just about satisfying curiosity, though curiosity is a powerful and worthy motivation. It is about expanding the boundaries of what we know and what we can know. It is about pushing back against ignorance and uncertainty, replacing speculation with knowledge, and it is about demonstrating the power of the human mind to grapple with questions that seem impossibly large and still make progress. The universe is vast, complex, and often baffling, but it is not inscrutable. Through careful observation and rigorous reasoning, we can uncover its secrets. The question of whether space is finite or infinite is one of the deepest secrets there is. It goes to the heart of what the universe is and how it works, and we are closer than ever to finding the answer. When that answer comes, it will be a triumph of human intellect and determination. It will stand as a testament to our ability to understand the cosmos despite our limitations. And it will open new questions, new frontiers, new mysteries to explore. That is the nature of science. Each answer leads to new questions. Each discovery reveals new horizons. For now, we live in the uncertainty, in the space between what we know and what we do not yet know. But that space is not empty. It is filled with effort, with exploration, with the relentless drive to understand. And as long as we continue to ask questions and seek answers, we move forward, step by step, toward a deeper and more complete picture of reality. The universe may be finite or infinite. Space may have an edge or extend forever. But whatever the truth turns out to be, the act of searching for it is one of the most profound expressions of what it means to be human. We look up at the stars and ask why. We peer into the depths of space and time and demand answers. And slowly, painstakingly, the universe begins to respond. That is where we are now, on the threshold of understanding. The tools are in place. The observations are being made. The calculations are being run. And one day, perhaps soon, we will know. We will know whether the cosmos is a finite, bounded structure or an infinite expanse. We will know whether space has an edge or continues forever. And that knowledge will change us just as every great discovery has changed humanity throughout history. The universe is waiting to reveal its secrets, and we are ready to listen.